All right, so I'm going to try to go through this video as quickly as possible. You do not need to copy down these notes for this. I just want you to kind of look at it. This section isn't really as important. That's why I tried to line it up for Friday. It's important for you to understand, and you will have questions about it, but it's not quite as important for you to necessarily copy this down. It's more kind of seeing these examples, right? I said before, data is never perfect. There's not usually one right answer when we're talking about data and analysis. There are different ways we can do it. We can use a linear regression, but sometimes we could use an exponential regression, and that might fit our data even better. So for the warm-up, I just want us to kind of think about what different information we can gain from each of these. So the first one is just the table of values of data points, of the data specifically. So like that frozen yogurt data compared to the temperature outside. Really from there, all we can do is we can just kind of see the results. That's really all we can do. Maybe we could draw a graph as well, but we can't really make any predictions yet. Once we have a scatter plot, right, that is our graph, then what can we do with that? We still can't really make any predictions. We can see the results graphically. Sometimes that's nicer. And we might be able to draw a best fit line. And we call that a regression line if we use a computer to do it. Once we have that regression line in its equation, then now this is where we can go and we can make predictions. And so that's pretty important, is to get to that step so that we can make predictions about our data. Then yesterday we talked about these residuals, right? The residuals were how far apart the data was from our regression equation. So if we had a table of residuals, we can basically see how far the actual data is from our predictions. And then we can also graph this, right? We can graph it. So we can draw a residuals plot. And the residuals plot, right? Make sure it's the residuals plot, not the actual data plot. It doesn't tell us anything about the data. It just basically tells us, we can use this to see if a linear or a nonlinear model is the best. Right? So we said if there was no pattern, or if there was a flat pattern, we would do linear. And then if there was a curved pattern, we would do nonlinear. So jumping into this, we have four data sets to take a look at. So we have four data sets that we're going to look at. And each one of these data sets is a little bit different. You don't have to graph these. I already did it for us. So here is graph 1, graph 2, graph 3, and graph 4. And so I went in and I did the linear regression for each of them, that equation. The y1 is approximately m, or regress to mx1 plus b. And for each one of these, I got m was 0.5 and b was 3, and I got 0.8164. All of them were the same, 0.816, 0.5 and 3, 0.816, 0.5 and 3 if we round that, and 0.816 and 0.5 and 3. So all of them had the same regression equation and the same R, the same correlation coefficient. So they all had the same results there. And so when we look at the graphs, though, they're definitely not the same graphs, right? Those were very, very different graphs, right? We had this guy is so much different than this one, which is kind of more of a curve. And this guy looks like it's, kind of almost linear, but more just, in a pattern. And this guy looks very linear, except for that one point's just a little bit higher. So they're all different shapes, right? And so we want to kind of think about that. And this mathematician, Francis Anscombe, he made a suggestion. He said it's very, very dangerous to only rely on the analytic sides of statistics without actually looking at our graphs, right? If all we looked at was the y equals 0.5x plus 3 and the r equals 0.816, we would think that these data sets are all the same. But when we look at the graphs, they actually look very, very different. Okay? Next, we're asked to calculate the average of the x values in each data set. Remember from middle school math, to do the average, you take all of the numbers, you add them up, and then you divide by how many there are. There are 11 numbers here, so we would add up these 11 numbers and then divide by 11. So I did that for us. You don't have to do it on your own. I already did it with the calculator. I got 9. And actually, Desmos has a really neat way of doing it for us. So on Desmos, what we can do is once we have our plot, we can go to a new line and we can make it go to this functions button. And under statistics, under stats, there's a button that says mean. Remember, mean is just another name for the average. So I'd click mean, and then I would type in x1, and it gives us the answer of 9. Do the same thing for mean, and then type in y1, and I will get 7.5. So I did this for all of them. I got 9 and 7.5, 9 and 7.5, and 9 and 7.5. So all 4 of these data sets, they also had the same average for our x and for our y. Now you'll notice I wrote this a little bit different. I wrote this with this x with the bar over the top. That is just the mathematical symbol for the mean of x. So whenever you see your x bar like that, that means the average or the mean of x. So that's what the symbol is. So what does all of this data tell us about the similarities and the differences in our data? Well, they had the same regression equation and they had the same mean, the same average, but they were very different graphical shapes. So next we're asked to construct a scatter plot and think about what the scatter plot says about our data. So you don't need to plot this. We're going to just kind of look at the Desmos graphs. And so looking at our first graph, we have our scatter plot. Here is our regression equation. And I would say this is probably appropriate, right? The R is 0.8, which is pretty close to 1. And the graph looks like it matches a linear pattern. It looks like a linear pattern. So I would say this definitely looks appropriate. When I look at the second graph, it looks more curved. I would guess it's probably not a linear would be the best option, right? The linear kind of is close, right? If we look at 0.8 as our R, it's close, but it doesn't quite look linear in shape. It looks more quadratic. And so this is where I want to go back to that interpolation versus extrapolation. Okay, if we were going to do interpolation, it would work on this guy, right? All of the points in here are pretty close. Here, interpolation would work pretty well. All the points are close. But if I wanted to do extrapolation, like if I wanted to take a guess for what this graph would be at 35, okay, at x equals 35, if we type that in, oops, x equals 35, there we go, we would get a prediction of 20.5. But if I look at this graph, I'm thinking it's going to not be 20.5. I'm thinking it's going to be negative somewhere. So this would not work very well for extrapolation. I don't think it would. But on this graph, I think that for x equals 35, I think that the pattern looks like it's kind of going to be the same. So I think that, that guess, and since the equations were the same, I'm guessing that our estimate will be very similar, right? 20.5 and 20.5. That makes sense because it had the same regression equation. That purple line is the same. And I'm thinking that the pattern probably will be somewhere around 20.5. It might not be exactly 20.5, but I think that'll be a good guess. So what happens is, that's why it's important to think, does this fit a linear model? If it does, then extrapolation is safe. We can probably do extrapolation pretty safely, right? Whereas here, I don't think we could extrapolate this graph to 35. I think kind of going outside of the data with this linear line would not be safe. But if we zoom in, right, the points are all close to the line. So anything that we're doing interpolation for inside of the data is okay. So that's kind of the difference between extrapolation and interpolation and why it matters for us to pick a graph that matches our data set. Okay. So next up we have this guy, right? And I would say, again, this is probably a good linear model. It looks like it's forming somewhat of a line. Right, there's one kind of outlier point, but overall it's forming a line. And then what about this guy? So this guy is probably not a line. The reason why it fails the vertical line test, right? This is a vertical line. So I don't think really any model would be too good for this. This is just kind of some weird data that's not really a function. So it's hard to model it with a function since it's failing the vertical line test. So that's just a little bit about each of those four. Okay. Let's flip back over here, and we're going to look at another model. And so this is a table of CDs sold in the United States since 2000. Okay. So CDs sold in the United States since 2000. And so I graphed this again on Desmos for us. And our graph looks, let me kind of zoom out so we can see it so my face isn't in the way. So our graph kind of looked like that. So that was the shape of our graph. Okay. And so based on this scatter plot, I wouldn't really think that this looks too linear. You know, maybe a line would work out well, but it looks like it's got a little bit of some curving going in, right? Now, why do we think this about CDs? Well, you know, CDs were very popular, right? In 2000, they were very popular. But around 2000, iPods started getting more and more popular. The iPhone wasn't even out, but iPods became popular and people were listening to music on iPods, right? And so they were listening to it digitally instead of, you know, on a CD, right? And then, you know, somewhere around here, right, iPhones came out, streaming services came out, and it decreased even more. But now it looks like it's starting to level off, right? You know, it's not as popular, but it's kind of leveling off, right? It's not going to go through and pass through to zero. You know, some people still buy CDs if they need it for a specific reason, right? Maybe they're older and they're not used to streaming services, or maybe they need it for, you know, a company, right? Sometimes companies want to have like the actual physical CDs so that they can play it at certain events where they know that the internet won't be reliable. And so, you know, that's, you know, there are still people who buy CDs, but it's kind of leveling off. My guess is that eventually it'll kind of level off to zero and CDs will disappear, but it's never going to go negative, right? So a linear model is probably not the best here. It's probably kind of curving down, right? And so we want to, you know, figure something that's not quite linear would be my guess there. Okay. Now we can still, you know, calculate a best fit line and just see what the best fit line would look. So this would be our best fit line. It does have an R of negative 0.97, which is very close to 1, right? What does that negative tell me? It tells me my graph is decreasing. And, you know, based on this correlation coefficient, right, and this is what the questions asked us over here, based on the correlation coefficient, you know, R is very close to -1. It should match our data very well. Now, R being close to -1, I want to be careful about this. It doesn't mean that linear model is best. It just means that the data will be very close to our regression line, right? So the data is very close to our line. But it doesn't mean that the line will work forever and that it's the right shape. Okay? Now, let's use this line to, you know, kind of predict the amount of CDs. So this is something that I definitely want us to know how to do. We can do this two ways. One way of doing it is to just type in x equals 2007, which here is just 7, right? X equals 7, and to get that point, 7570. But another way to do it that I like better, if we're going to do a lot of these, is to come up with, you know, a function. So I did f of x equals 856.025 plus 13,562.2. That was my y equals mx plus b. And then I can do f of 7, and I get that same answer, 7570, right? 0.025. I got that same answer. So we would predict that in 2007, 7,570 CDs would be sold. Right? Then we could do the same thing for f of 15, right? 721 CDs. And the same thing for f of 25, negative 7,000 CDs. So, you know, 721 and negative 7,838. So we can kind of see that, you know, the 2007 data, right, around, you know, year 7, looks like a good prediction, right? And even the 2015 prediction, you know, around 700, looks like a pretty good prediction. But the 2025 prediction is negative. That doesn't make any sense, right? So we're thinking, you know, based on that prediction, that, yeah, maybe this prediction is kind of hinting that a linear model isn't the best model. Okay. So we can do our residuals and all of that, but I'm going to kind of skip that. We've done this a lot. Just as a reminder, though, the way that you would do this is, if I wanted to do this, I would go into Desmos, and I would do my f of 0, right? So I do f of 0 in Desmos. Let me show that really quickly. So f of 0, I get 13,562, right? So 13,562 was my predicted value. And then I would subtract these two numbers, right? I would subtract these two numbers. So 13,562 minus 13,215, right? And from there, let me get a calculator. 13,562 minus 13,215. That's 347. So the interpretation of that would basically be that, 347, and actually it's negative, right? It's negative because we want to subtract this number first. 13,215 minus 13,562. So we'd say 347 fewer CDs were sold than the prediction. Right. Now, we could fill out this table, but it's just kind of tedious to do that, right? I think that we kind of get it. So, oops, I think I'm sharing the wrong screen. That's my fault. So anyways, we got the 13,562. And so what I was showing is in the table, we were predicted for that. If we subtract these two numbers, we get negative 347, and that means 347 fewer CDs were sold. I'm going to go ahead and skip the table. I don't think we really need to worry about it too much. But we could go ahead and create a residual graph from this. And when you create a residual graph from this, we will get something that's curved. We'll get something that's curved, right? And so that's going to tell us even more so that we probably don't want to use a linear model. Okay, but I'm going to go ahead and skip that. I think we've done that a lot. We did that for homework, right? And we're going to do that a little bit more for homework tonight. So, kind of looking at nonlinear regression, what else might we try? And so the textbook kind of suggests, hey, why don't we try this cubic function? Why don't we try this cubic function? And so I went ahead and put that into Desmos already. And so here is what this cubic function looks like. Now, if I zoom in, I think the cubic function looks pretty good. Okay, it looks like this red line is, for the most part, closer to most of the points than the purple line. Not to all of them, but it looks pretty good. But again, if I zoom out, it doesn't really look good at all. So that may not be the best, kind of long-term play. But sometimes in life, things happen where it's very hard to get an actual equation that's going to really, really help out because, like I said, eventually the CD market's just going to die and it's going to go to 0. So, we might have a different model after streaming than before streaming. And so that's something that, we want to consider as well. So that's most of the notes for today. Really, I don't really want to touch on too much more. Is, that's kind of what happens. I do want to kind of maybe look at, if we did decide, okay, let's try to use this red function, we could also use that. So we could, I type this into Desmos, and we could make those same predictions, right? We could make those same predictions for the year 2007, right? For the year 2015, and for the year 2025. I don't know why in your textbook they changed the 2007 to 2005, but I left it as 2007 because that way we could kind of compare, right? And so my prediction was 7,557. That was from the prediction from the purple line when I did f of 7, right, with the linear regression. When I used this cubic one that the book suggested, I got 7,490, right? That was my prediction for year 7, which is about right here, right? And they're very close to each other. On year 15, I got a much different prediction, though. On year 15, the purple line at year 15 gave me 721 CDs, but my red, kind of cubic function gave me, at year 15, 1,000 CDs. It gave me a little bit different. It gave me a higher prediction at year 15, right? And if we're kind of looking at the data, I'm not sure which one would actually happen, but, it is a little bit different. And then at year 25, the, if we go to the extrapolation, year 25, the purple, the linear line, gave me negative 7,000 CDs, and the red one says somehow 13,500 CDs more than were ever sold are going to be sold. So I don't think either one of these really is the best option, but it's just kind of looking at, different regression equations than linear and what might happen when we have different equations than a linear equation. So jumping over to our homework,